For those of you who are unfamiliar with how an alternator works, I'm going to do my best to give a fairly simple explanation of the whole thing so you'll understand why I'm tearing my new alternator apart and modifying the way it works. Alright, so typically, I mean, this goes all back together, you know, and you've got a belt coming from the engine that goes around here and it turns that. And that turns this part here. This is called the rotor because it rotates. Now, if you take copper wire or any conductor and you pass it through a magnetic field, the magnetic field will cause an electrical current to move in the wire. And if you take that wire conductor and you wrap it into loops, many loops, it'll amplify that effect. So if you pass a loop of conductor through a magnetic field, it will produce a larger current in the conductor. Now you could reverse the whole situation and pass the magnetic flux, the magnetic field, through or by the coil conductor, and you'll do the same thing. I mean, it's the same. So conversely, if you take a conductor and you make this loop and you apply electricity to it, pass a current through the looped conductor, it will create magnetism. It'll be an electromagnet. So in this rotor, you can see down in there and you can see the windings of copper wire. And those are connected right here and right here to these two copper rings called slip rings. That way, while this is spinning, electricity can be applied to those windings, making it an electromagnet. And because it's moving, something's got to just brush against here, which are the brushes. They call them brushes. They're right there, these things right here. They're spring-loaded, but I've got the springs out. And they brush against the slip rings, transferring electricity to the copper coil. Now, when you make a copper coil, you make a magnetic field in the middle of it when you apply current running voltage through it. And if you put a piece of iron through the center of that copper coil, it will create an even stronger, more focused magnetic field. I'm not sure why. I mean, I know there's reasons. I'm just not an expert on this stuff, but it happens. So on here, what you've got is you've got this iron core that wraps up around and that comes to the outside. You've got one coming from the one end and one coming from this end of your magnetic field. So that electromagnetic coil in there is producing a north pole and a south pole, and they're bringing them around with these little tabs so that this is north, south, north, south, north, south, goes all the way around. So as you spin it, you're getting this change in magnetic field rapidly. I mean, it's happening very, very rapidly. Okay, so we'll put that aside. Now this here, this goes around that whole rotor. And so you've got a magnet. You've got an electromagnet that has transferred its north and south poles out to its edge. And you run that through here. And then you have all these copper coils right here. And when you run that magnetic field around through here, these coils, that magnetic flux induces a electrical current that flows through these coils. Now, all these coils, there's three rows. I don't know if you can see that. There's an inner, a middle, and an outer row of these. So there's three different circuits on this. And you can see their outputs are right there. And so as that thing is spinning, it's actually producing three different electrical currents in these three different sets. You see three different circuits of coils. Now these sets are set 120 degrees out of phase in rotation with each other. So as that thing is spinning, you start to get these three separate currents and the electric flow is alternating because you remember we've got north, south, and as that spins, I mean, it's reversing the electrical current in these coils back and forth, back and forth, back and forth. Every time the magnetic polarity changes, the electrical polarity changes. So you end up with alternating current. The type of electricity that you put into this electromagnet is direct current. The electrical current flows in one direction, positive to negative. And in here, it's alternating back and forth, back and forth. That's why they're called an alternator. So each of these circuits right here, they are all changing their polarity directions in voltage from the peak positive down to peak negative, and it makes a sine wave. Let's see, a sine wave up, peak positive down to peak negative. And these are all three happening simultaneously, but 120 degrees out of phase. That way your peaks of positive and negative voltage don't line up exactly at the same time, or you'd have this very strong fluctuation in your electrical voltage. So you spread them out, and it kind of evens it out. Okay, now to get that, and that's called three-phase. So now you've heard that term, three-phase. There's three different phases of electrical current being induced in these coils. So this goes into here, and those three wires hook down to these little posts. Inside here are these semiconductor devices made of silicone that are called diodes, and a diode only allows electric current to flow in one direction. So down in there's actually 6 of them, 2 for each circuit of the three-phase alternating current. And the reason there's 2 is if you only have one diode and you run alternating current to it, it's just going to cut off. You can only hook it. It's only going to it's going to filter out all the negative part of the sine wave, or it's going to filter out all the positive side. Well, you want both of it. You want the full potential of it instead of just having it cut off half your power. So they use a diode to filter the positive part of the sine wave and send it out as a direct current, and then use another diode to filter out the negative side of it. But they aim them in the same direction, so you end up with a pulsing, basically, that's all the current flow going in the same direction. They do that with all 3 of the phases. So in the end, the output of the alternator ends up being a very high-speed pulsating DC current, and it's not. It's clean enough for what it's used for charging batteries. Basically, it's clean enough power. If you need some very, very, when I say clean, it means like the power that comes out of the wall plugs, that is alternating as well, and it's set at a specific phase. I'm not going to get into this. I'm making it too complicated. You can go read on that if you want to. Let's go back to the alternator. So, if you want to increase the power output or decrease the power output, which is going to be read from the alternator, it's going to be measured in voltage. So if you want the voltage to go up, you increase the magnetic field in the rotor. If you want it to go down, you decrease the voltage. It makes the electromagnet stronger or weaker. You can also drive the rotor faster or slower, but for what we're doing, that's not practical. That's why there's alternators on cars now instead of generators. Generators really only worked well at a specific RPM range, and an alternator will work all the way across the spectrum within reason, because you can vary the voltage on the rotor, and that's the job of the voltage regulator, which is this device right here. There's electronic components inside, and I haven't cut it open yet. I actually need to cut open the housing because I'm going to do some modification, and I'll film that too. So how this is working is the voltage regulator is there's a lead that goes to it that can read output voltage of the alternator, or better yet, it can read the voltage at the battery. So if the battery is low and the voltage is low, the voltage regulator will read that, and it will say it will allow more